Hello guys, this lecture is about the moment of inertia of solid and hollow cones. Now here in the first one we will be deriving the moment of inertia of a right circular cone which is a solid cone about its altitude. Now first of all, what is a right circular cone? That is our concern here. What is a right circular cone? So right circular cone means it is not oblique, means if we draw a line joining the apex to the center of the base, then it will make 90° with the base surface, then we call it right circular cone. Otherwise there are some other types of cones like this, they will be told as oblique cones because this angle will not be 90°, this will not be 90°, it will be called oblique cone. So here we are finding moment of inertia of a right circular cone about this altitude, means about this height axis we are finding. Now let's find out. Here, as this is a dense object, means the material is all over the matter here, means all over the object here. So in that case we will follow the volume charge density, means volume mass density, means rho value we will be following. Now what will be the rho value? This will be total mass by total volume, because this is volume mass density, right? So mass by total volume. So mass is m and volume of this cone is 1/3 pi r square h, where r is the radius of the base, this is r value, and h is its height, this is h value. Now this is our rho, we defined rho. Now here we need to do integration, right? So let's, from the apex at a distance x, we will be choosing a very small disc kind of structure. So this element will behave as a disc, right? Now we have a disc like this whose thickness, this thickness is dx, and let's say this disc's radius is r. Now our axis is like this, it is passing through the disc like this. In this case the moment of inertia formula for this disc should be half dm, which is the mass of this disc, into r square. It should be like this, right? Because the moment of inertia of a disc about an axis passing through its center and perpendicular to its plane, the formula is mr square by 2. Here m, for this disc we are writing m as dm value, and the radius is small r here, so that's why we will write dm into r square by 2, right? So for this structure this is small dm into r square by 2. Now let's find out what is dm here. Now first of all, to find dm we will write rho into volume of this element, which is dv. Now rho value we have already calculated here, this is our rho value which we have already calculated. Now we are calculating the dv value. Now what is dv? Now this thickness is dx, right? And the radius is r. So the density, the volume will be pi r square into dx. This is the volume, that's what we have written here, pi r square into dx. Now the problem is we are integrating with respect to x here, but the variable we have is in terms of r, because this disc has this much radius. If we take another disc here, it will have a different radius r dash. So each element will have different radius r dash, and our variable is with in terms of x, dx is the integrand here. So let's convert this r into x term. Now see here, if we draw this triangle, this small triangle, this will be our small r and this is x. Now if we draw this large triangle here, this will be capital R and the total height is h. Now we can apply similar triangle principle here for these two, and we can write small r by capital R, this small r by capital R equals x by h value. This is x and this total value is h. From there we get r equals x into r by h. Now this x into r by h we will put here. So we have put here m by 1/3 r square h into x square r square by h square dx. Now see, the capital R term is constant, yes, this is constant. This h value is also constant for the cone. Only variable is x square and dx, x square dx. Now we can integrate it easily. So our dm value is 3m x square by h cube into dx. This is the dm value. Now moment of inertia, as we have discussed, it should be half dm into r square, right? Now we need to integrate this one. So we have written here the moment of inertia of the element di equals half dm into r square. Now half value, this dm value we have put here 3m x square by h cube into again small r came. Now small r value we have put again here. This is our small r value. Now putting this value, we are getting m r square by h to the power 5 into x to the power 4 here. So our integration value will be of x to the power 4 dx. Now integrating x to the power 4 dx from 0 to h, because here this x, this is the variable, this x is the variable, and it varies from here. It starts from here where h will be 0 and it ends here where height will be total h value. So we are integrating from 0 to h. So here we have integrated from 0 to h. So we are getting x to the power 4 dx integration is x to the power 5 by 5, and putting the values of h, here the h part cancels out and we are getting 3 by 10 into mr square. This is the formula for moment of inertia of right circular cone about its altitude. Now let's see for a hollow cone. Now this will be a tricky one, because in hollow cone only mass resides only on the surface. It doesn't lie in the middle area, in between the in the center of the object there is no mass. The mass is only on the surface. So we are taking element this way. Here from this point, let's say at a distance x, we are going along the incline. At a distance x, we are choosing a very small element dx. Now if we cover this element entirely for the entire circular path, then technically we will be getting a ring kind of structure, and again the radius of the ring is r and the thickness of the ring will be dx. Now here, as matter is not throughout the object, we will not consider rho here. Here only on the surface mass resides, that's why we will consider surface mass density, which is sigma. This will be m by area. Now m by area, let's put it here. So our sigma value is m by total curved surface area. This is sigma by m into pi r into this slant height L, and L value will be, let's say this is r and this value is h, then L value will be r square plus h square root over. So that's what we have put here, pi r L. Now from this, again we need to find the radius r here. Now again by applying similar triangle principle for this triangle and the total triangle, we are getting r by x equal to capital R by r square plus h square. Here we have taken this value, this is our x value and this is r. This total length is L and this is our capital R, we have put here. So we have used L here to find out. So we are getting small r value is rx by r square plus h square root over. Now we will be integrating this mass of ring, the small element, ring element. Now here the ring's area, ring is radius r and its thickness is dx. So we can write the area of the ring can be written as dA equals to 2 pi r, which is the perimeter, into thickness dx. So r value, after putting the r value, we are getting 2 pi r into dx. This is the area value. Now mass of the small ring dm will be sigma into small area dA. So sigma value we have already calculated, m by pi r L into dA value. This is the dA value. So we are getting dm value is 2mx dx by r square plus h square. Now let's calculate the moment of inertia. Now for this element, for this dm mass, for this small ring portion, the formula for moment of inertia for ring, formula is mr square. So here m is dm for this small element into r square. Now putting the value of dm and r, we are integrating total I equals, see here there is a one x square term, here one x term, all other terms are constant terms. So we are integrating x cube dx, and our limit is from this point till the end of this point. So here at this point x will be 0 and here at this point x will be L, which is our r square plus h square root over. So this is our limits. So 0 to r square plus h square root over. Integrating, we get x to the power 4 by 4, and by putting the value we are getting half mr square, which is the moment of inertia of a hollow cone about its altitude again.